All right, so we're on to transfer functions. So let's get started with transfer functions here. So what is a transfer function? Okay, so first I talked previously in the intro about how we've kind of seen transfer functions already, but we probably just don't realize it. So let's say I have a circuit that looks like this. And some signal here is my input V in of t. And I've got a resistor here, right, just like this. We'll call this R1 and we'll call this R2. And then I've got some output voltage here, V out of t, that I'm interested in. And of course, you should be able to recognize this pretty quickly as a voltage divider, which we already know the equation for the voltage divider, which is V out of t would be equal to the input voltage, V in of t, multiplied by R2 over R1 plus R2, just like that. So that's nothing new. So what is a transfer function? Well, a transfer function, according to the textbook definition of the transfer function, it is a ratio of the output, some output that we're interested in, to some input that we're interested in. And so in this case, the input to this circuit that we're interested in is V in of t, Vi of t, and the output that we're interested in is V out of t. Okay, and so if we're interested in that ratio, all we have to do is divide both sides by V in of t, right? If I divide this side or multiply this side by 1 over V in of t, then these will cancel. And I multiply this side by 1 over V in of t. And so what I'm left with is this expression here, V out of t divided by V in of t is equal to R2 over R1 plus R2. And there we go. That's my transfer function right there. It is the ratio of the output of interest to the input of the circuit. And so in this case, it was just V out over V in, happens to be R2 over R1 plus R2. And so this is how we find the transfer function. Typically, I'm going to go into how do we find a transfer function later and do some more examples, but we've kind of already seen it. It's really just taking the expression that we already had for the voltage divider, right? Which I've canceled some of the terms now, so it's messy, but it's basically this equation right here. And I just divide both sides by V in of t, and now I have the transfer function, V out over V in. Right, so again, let's say I can generalize this to any impedances. Right, this could be an impedance here, and then this could be another impedance here. Doesn't necessarily have to be a resistor. It could be any impedance, so I'll call this Z1 and this will be my Z2. I'll call this Vs of t, and I'll call this one V out of t. In fact, let me write these as phasors. I don't actually need to write these as, this could be Vs, just capital, kind of bold Vs here, and this can be V out. So those are not functions of t now. Let's just say that those are phasors. So again, I can just go right to my voltage divider equation and say V out is equal to Vs times Z2. I guess I should go back to the small pen for these impedances. Z2 over Z1 plus Z2. And then, of course, I can rearrange by dividing both sides by Vs, and I get V out over Vs is going to be equal to Z2 over Z1 plus Z2, and that would be my transfer function for that circuit, right? So this one I did in time domain, this one I did in the phasor domain, but they basically give us the same expression. These are just impedances, and these ones are resistances, okay? So pretty straightforward for what the transfer function is. Again, it's just the ratio of the output to the input. These are very simple circuits. Of course, this can be generalized to much larger circuits, much more complicated circuits. And so in the next slide, I'll take a look at kind of what the book has for transfer functions. And I'll actually just go ahead and read the textbook definition. This is on page 614. So let me write this. Page 614 of SATIQ textbook, 5th edition. Of course, I've linked the textbooks in the web page. But what the definition says is what the transfer function is. What is a transfer function? It says it is the frequency dependent ratio of a phasor output Y. So we have our phasor output here, right? The frequency dependent ratio of a phasor output Y, it can be a voltage or a current, to a phasor input X, which can also be a voltage or a current, okay? And so here we have the transfer function written as h of omega. They're using angular frequency here. Of course, we could convert that to hertz. Omega is equal to 2 pi times f. Just keep that in mind. But we can always convert back and forth between frequency in hertz and frequency in radians per second using this equation here. But just one more time, that definition, by definition, it says the frequency dependent ratio. So again, here's the ratio of a phasor output Y. It doesn't necessarily have to be the variable Y, but they're calling it Y because they're referring to this figure. Frequency dependent ratio of a phasor output Y to a phasor input X. Okay? And so in this circuit, I've got some input X, I've got some output Y, and my transfer function is the ratio of Y over X as a function of omega in this case. So for the case where I have, a circuit here, and this is my input, and this is my linear network here, and say this is my linear network, and let's just say again that let's say that it's like a resistor here, a capacitor here, and I'm interested in some output V out of omega, and here I have V in of omega, right? This would be R, this would be minus J over omega C. And of course, we can go through here now, and we can use the transfer function, or the voltage divider equation, to find the impedance of the resistor, the impedance of the capacitor, and we can write an expression here for the ratio of some output, which in this case is going to be V out of omega, to the input, V in of omega. And of course, we know that that's going to just be Z2 over Z1 plus Z2, exactly like we found on the previous page right here. And then from there, all we'd have to do is plug in our impedance values and simplify and rearrange things. And that would be my H of omega in this case. Because of course, this impedance is dependent upon omega, so we're going to get some function, H of omega, or V out of omega over V in of omega, which is going to have dependency upon omega, okay? And so I'm going to go ahead and stop this video here. Just wanted to introduce the transfer function. I might even be making it seem more complicated than it is. It's really just another way to represent basically in the past when we're talking about the voltage divider equation, right? V out is equal to V in times Z2 over Z1 plus Z2. It's just the rearranging of this equation to get a ratio of the output to the input on one side of the equation, which is exactly what we see here, and that's exactly what we see here. Okay? So as far as we're concerned, it's just the ratio of the output to the input. The output can be whatever output we're interested in. In this case, I've been strictly interested in voltages. We could pick some current that we're interested in and make that our transfer function, and so on, okay? But for now, let's just leave this video here. I'm going to go ahead and put a box around this. And let's call it, we're just going to go ahead and end this video here. And in the next video, I'll continue on about transfer functions.